Exactly.
All right, welcome everybody. Good evening. I am so happy to see everybody here, and thanks for your patience. We had a really quick changeover from a classroom into this fantastic event. So I'm really glad to see a packed house for what's going to be an incredible lecture. My name is Pearl Sandick, and I'm a professor of physics and astronomy, and I'm also the interim dean of the College of Science. On behalf of the College of Science, I'm really happy to welcome you to this Frontiers of Science lecture, which is the first one of the Frontiers series in the Grant C. and Norma M. Parsons Auditorium in our brand new LS Skaggs Applied Science building. We have a fantastic presentation for you today from Katherine Freese entitled The Mystery of Dark Matter in the Universe. And in a moment, Dr. Freese will get a proper introduction. But I want to start with a few comments about this beautiful building we're in and a little more about the lecture series itself. As some of you may remember, we opened the LS Skaggs Applied Science Building in July of this year. I know a number of you were here for that event as well. And since then, this building and the adjacent renovated William Stewart building have been a really vibrant hub of activity for students, faculty, and staff from across the college. This facility serves as the permanent home of the Department of Physics and Astronomy, the Department of Atmospheric Sciences, and the Wilkes Center for Climate Science and Policy. With over 140,000 square feet of classrooms, student spaces, laboratories, and more, and together with the Crocker Science Center, this space completes the Crocker Science Complex. And as you can see, this really incredible space demonstrates how we're bringing together world-class research and education, addressing global challenges, and seeking answers to some of the biggest challenges in the universe. We wouldn't be standing here today without our generous donors to this project, Gary and Ann Crocker, the Alsam Foundation, and tonight we really appreciate Ronnie and Lindsay Cutshaw for being here, Don and Rebecca Reese, who supported the beautiful laboratory classroom on the 4th floor that you'll see later this evening, I hope, and the Eccles Foundation, who supported the Willard Eccles Astronomy Observatory on the rooftop of this building. And tonight, we hope we'll be able to see some stars after this lecture. I also want to thank all of the other donors and people who are here today who contributed to this project. It was a huge effort, and we would not be here without you, and I just really appreciate that. So let's give everyone a round of applause. And for those of you coming in, there are still a few seats down here if you want to come all the way down to the front. Okay, so we're here tonight for the inaugural Frontiers of Science lecture in this new space, but the Frontiers of Science lecture series is the oldest and longest running lecture series here on the campus of the University of Utah. It was started in 1967 by a physicist, Peter Gibbs, and his idea was to bring forefront researchers from around the world right here to our campus to present public lectures that would attract attention to important topics and developments in scientific research. The title, Frontiers of Science, is a nod to a famous white paper that was called Science, the Endless Frontier by Vannevar Bush, which he wrote for President Roosevelt in 1945. And in that report, he laid out the rationale for why basic scientific research is so important and why we should fund it. And it was also, that served as the foundation for the National Science Foundation. Over the years, Frontiers of Science lecture series has attracted many distinguished visitors, including 25 Nobel laureates, the most recent of which was Stephen Chu, who was here in February. I think some of you were in that audience as well. Okay, without further ado, tonight I have the great pleasure of introducing my friend and colleague, Dr. Katherine Freese. Dr. Freese is the Jeff and Gail Kadalski Endowed Chair in Physics and a professor of physics at the University of Texas at Austin. She also serves as the director of the Weinberg Institute for Theoretical Physics and the Texas Center for Cosmology and Astroparticle Physics. She's known for her work on a wide range of topics in theoretical cosmology and astroparticle physics, and has been working to identify the dark matter and dark energy that permeate the universe, as well as to build a successful model for the early universe immediately after the Big Bang. She's also the author of a book, The Cosmic Cocktail, 3 Parts Dark Matter, which came out in 2014. Freese has received a number of awards and honors for her work. She's a fellow of the American Physical Society and was awarded the 2019 Lilienfeld Prize for groundbreaking research at the interface of cosmology and particle physics, and for her tireless efforts to communicate the excitement of physics to the general public. In 2020, she was elected a fellow of the National Academy of Sciences. Please, let's welcome Dr. Freese.
Well, thank you, Pearl, for that lovely introduction. So now I just have to find, here it is. Let's see, something has to change. Cross your fingers. Uh-oh. Okay. Let me see, the laser pointer works? Yes. So before talking about modern cosmology, I always like to think back about what it must have been like in the days of antiquity. Those people weren't any different from us, and they must have asked a lot of the same questions. What is out there? How did all this begin? Where is everything going? They had creation myths. One culture after another, they all did, and then along comes the days of Albert Einstein, and we have our creation story, the hot Big Bang. The difference is that this one is correct. It's incomplete, but it's right. So in human history, that is a phenomenal achievement. So this whole field of cosmology only started 110 years ago with the work of Albert Einstein, who wrote down the theory of general relativity in 1915. Then not soon after, people took those equations and applied them to the universe as a whole, making some simplifying assumptions about what the universe should look like on large scales. And when they did that, they realized that there were three possible shapes for the universe and also three possible behaviors of the universe, ways it could evolve. It could be expanding, it could be contracting, it could be static. Einstein was the fan of a static universe because that would have meant even more symmetry, that it's the same at all times on the average. But, well, nature is not always the favorite of theory, doesn't back what you want, it just does what it does. And so in 1929, Hubble discovered that the universe is expanding. He was using the mountain, in the mountains, yeah, they're actually mountains above Pasadena. They're the telescopes. And yeah, you know how I discovered this? Because I had a sabbatical at Caltech where you bike up them, you're like, holy, whatever, what is this? Well, it's the same vertical drop as Aspen, just so you know. So no, I didn't make it all the way up. But anyway, so he made major advances of many types, but one of them was looking at, well, first of all, he was the one who who proved that there are galaxies besides our own. Until then, people weren't sure about that. They thought the Milky Way might be it. And then looking at those galaxies and observing what they do. And one of the things he did in order to do this is look at light that comes from stars inside these galaxies, and you know what those atoms do. So you know what the length of the waves is that comes out of those atoms. And you measure it here today, and guess what? The wave had stretched. Well, you can see from the analogy with the balloon what that could mean. If you're blowing up a balloon, the balloon expands, and that is what causes that wavelength to stretch. So so you know this wavelength, you measure that one, and you conclude, well, the universe must be expanding. And yep, there goes goodbye static universe preferred by Einstein. Very simplistic picture. On the average, galaxies are moving apart from one another, okay? Now, obviously, inside our galaxy, gravity wins, and we're contained here. We're not flying apart from one another. So I'm talking about very large scales. This is kind of a simple little image, the raisin bread model of the universe, where you assume these raisins they're mock-ups of galaxies, and if you take the dough and put it in the oven, then the whole thing rises. Has anybody done that? I haven't. Okay, so I believe it makes sense. Anyway, and so the raisins move apart from one another, not because they're doing anything, it's just that the underlying bread is expanding, and that's the way to think about it. But one very major difference between the raisin bread and our universe is that a raisin bread has a central point. We don't think our universe does. There is no special place in the universe. If you go to any other galaxy in the universe, you also will see everything moving away from you. That's a big difference. I also wanted to address a misconception that a lot of people have that is perpetuated in the popular press, which is about the idea of what is the Big Bang. And okay, so to ask this question, let's go backwards in time. Then in that case, the universe would be contracting. Things get closer and closer together. Everything in this room would contract to a point. But, the universe could be infinite. Very, very possible. If it's infinite, then no matter how much you contract it, it's still infinite. You're not contracting anything to a point. It's getting denser and denser and denser, and when it gets dense enough, that's where our laws of physics fail, okay? And that's what is called the Big Bang. In fact, it was, who was it? Was it Fred Hoyle that called it that? And he did it because he thought it was such a ridiculous concept. And the name stuck. So the Big Bang is really a point in time, not a point in space. And so there's not really explosions either, but let's put one at every point if you want one. Well, where do we stand in cosmology? I've talked about the major advances in the last 100 years. But over the turn of this millennium, we've got other really even accelerated advances that are happening because of the flood of data that are pouring in from many, many different observatories. Big questions have been answered at the turn of the millennium, including what is the shape of the universe, its geometry? What is the total mass and energy content of the universe? How old is the universe? So we know an awful lot. But we still don't know, despite all this precision cosmology, what is the universe made of? What is the dark matter? What is the dark energy? So I probably shouldn't spend a lot of time on telling you how we know about the geometry of the universe. So I think I'm going to skip these slides, but this is something that I could return back to in the time of questions. Because I want the three possible geometries of the universe and how we discovered the answer that the universe has no curvature to it. It has a flat geometry. That doesn't mean it's two-dimensional. It just means that, let's take a cube, and you take all the sides out to infinity. That's the geometry you learned about in 8th grade, about parallel lines never meet, and so forth. So it's a very much simpler geometry than it could have been. But let me turn now to the subject of this talk, which is the content of the universe. And this is, it's a weird universe. I mean, so all the stuff that we're used to, your bodies, your chairs, the air you're breathing, the beautiful new building that we're in, the earth that we live on, the sun that we rely on, and all of that, as you know, made of atoms. I wanted to do this behind my head. That's kind of fun. And so, but all of this atomic matter only constitutes 5% of the universe. That's pretty bizarre. Well, we have to figure out what is going on here. And in fact, if we do take a pie picture of the universe, then there's the stuff we know about, the 5%, and then there's the dark side, dark matter being about 25%, and dark energy being the remainder, roughly 70%. So this is from my book, The Cosmic Cocktail, which I will also end with the same slide. And at that point, I'll tell you my recipe for the universe. But in the meantime, let's talk about the dark matter problem, which is now 90 years old. It dates back to a Swedish scientist named Knut Lundmark and a Swiss one named Fritz Zwicky in the 1930s. Now, famously, this is Fritz Zwicky, who also worked in the same mountains above Pasadena. And what he was looking at is a cluster of galaxies. A cluster that is a thing that contains hundreds of galaxies. And he was watching one of those galaxies moving around the center of the cluster. And you see how many other galaxies there are on the inside, and those are the ones that you think are providing the gravitational attraction that keeps that one guy moving around. But what he found instead was, whoo, it's going really, really fast, and it really should be just escaping off into space. Something is holding it in. And the idea is that's an additional matter that is dark, dunkle Materie meaning dark matter. And by the name dark matter, it simply means it's not stars, it doesn't shine. It is dark, it doesn't give off light. So after this work, I do want to tell a joke about Fritz Zwicky. Well, it's not a joke, a true fact. You can decide if it's funny or not. In his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. I have more stories, but I think I better move on. So after the 1930s, then there were many other data sets that came in, people arguing about this, what is going on. And it was really the work of Vera Rubin in the 1970s that nailed it. She basically proved that every single galaxy has dark matter in it. And that led to the scientific consensus that the dark matter problem is ubiquitous. Why she never got a Nobel Prize is a mystery to many of us. So I want to talk to you about what she did, but in order to do that, let's do an analogy to the solar system first. There's something called a rotation curve, which means you ask, okay, we start at the sun, and as I move to the right here, you're moving out to orbits that are farther and farther away from the sun. So you've got the orbits moving farther and farther away from the sun, and this is how fast the planets are moving. So, okay, the closest one is Mercury. It's moving the fastest, next Venus, then Earth, then Mars, da-da-da-da-da-da. And instead of getting rid of Pluto, the 9th planet, I added a 10th planet just for fun. Actually by accident, but there it is. So, and there's not a lot of equations in my talk, but I just thought I'd point this out. This is the speed of the planets, and what matters in determining the speed is two things. It's the distance away from the central object, from the sun, but it's also the mass in here that pulls on things. So if you have 4 times as much mass, things move twice as fast. And so it is a pretty simple argument that tells you if something's moving too fast, it's not leaving, that's because there's a gravitational attraction from something keeping it there. I just wanted to show historically some slides. This is Tycho Brahe. He made the measurements of the planetary orbits. And he was a character. He lost his nose in a duel and wore a gold and silver replacement after that. Yuck. And then the question was how he died, because we all heard that he died of a burst bladder at a dinner with the king. You're not supposed to get up before the king does, and he drank a lot of wine, and 3 days later his bladder burst and he died. Oh my God, I'm going to get carried away by stories. Well, I do have to tell you, they decided to check, was that really true, or was it his student, Johannes Kepler, who had poisoned him? The Kepler's laws really could have been maybe misnamed. Anyway, so they dug him up about 20 years ago and tested his mustache hairs, which there were still some, and there was no sign of mercury poisoning. So I guess the burst bladder story is true. And oh no, should I tell another story or move on? I don't know. The story, okay, so I got to go to some of the Nobel Prize events, the ceremony, the dinner, and da-da-da-da-da, and you're in your ball gown, and I'm sitting there off on the not on the main table where the laureates sit, off on a perpendicular table, and I had to go to the bathroom. So I went to the bathroom, and when I came back, I walked by the main table, said hi to somebody, and when I sat down, the woman across from me, who's on the Nobel Committee, said, "Well, if you're going to have to get up in the middle of the dinner, then at least you should do it more discreetly." So I totally believe in the burst bladder story. But I was not having it. Okay, so that was the solar system, but the same thing, we're going to do the same thing with galaxies. We're going to look from the center of the galaxy, move out a distance, some distance from it, and observe how fast things are moving. And okay, so the speeds here of things moving around the galaxy were going too fast. So again, you need additional material in there pulling it in. So this is the same kind of picture I showed you for the solar system, but this time it's for galaxies. And what you'd expect is, just like for the solar system, as you move out farther and farther from the center of the galaxy, that you get things slowing down. But no, look at this, they're really whizzing to way far out. So we have to add in, if you add in the dark matter halo, then it makes sense. All right, as an example, our Milky Way is our favorite galaxy, and let me tell you a little bit about it. Well, at the center is a big black hole that weighs 4 million times as much as the sun. It's just shown in yellow to make it visible. And I just thought I'd show that these two people won half the Nobel Prize for this discovery of this black hole. And the way it was done, this is an artist's rendition, is that you watch things moving around. It's exactly the same physics. How fast are things moving around tells you how much mass there has to be in there. And if it's a really ridiculous amount of mass, that's how you know it's a black hole. But supermassive black holes, I want to be clear, are not the dark matter. Every galaxy has one at the center, but they only make up a tiny fraction of the universe as a whole. So going back to the Milky Way, moving out from that central black hole, these are spiral arms, and most of the stars are along here. So here, for example, is the sun. Now we take this pinwheel structure and we look at it from the side, and here you go. This is called the disk of the galaxy, and the sun is 25,000 light years away from the center. And but this disk is just a tiny piece of the total galaxy. We have to go to an artist's rendition again for this, but there's the Milky Way, and there's this giant spherical thing around it that stabilizes it, made almost entirely of dark matter, and we call it a dark matter halo. I don't know the origin of that name. So in addition, well, at this point, the evidence for dark matter is there's a million pieces, and nobody argues about it anymore, that it has to be there, although we don't know what it's made of, but it has to be there. Here's another way to look for it, which is that when dark matter may not give off light, but it bends light. So this is, again, from Einstein's theory, that you get the bending of light. So if I have a star, the light bends around it on the way to the telescope. And so then naively you might think, well, I found something that's here because I didn't know that there was some mass in the way. But then you'd notice, wait a minute, I've got multiple images of the same thing, and they're sheared, they're weird looking. So what you can do is look at distant objects and look for this kind of behavior, and then figure out how much mass had to be in the way between, how much dark matter there is in the way between you and the distant bright object you looked at. And this is a massive compact halo object, but it doesn't matter. It's true for all dark matter. In fact, I used to be at the University of Michigan, and there's a graduate student who wrote an app for the iPhone with the correct equations of gravitational lensing, and you can lens yourself, okay? Students did this. He was my grad student. You can lens yourself more and more and more. But let's look at some real data from Hubble Space Telescope. There you go. And you've got distant galaxies that are bright, and something is in the way that's lensing that light, causing sheared multiple images. There's a massive amount of lensing going on in this one. I don't know all the details. But once you've got an image like this, then you can reconstruct using a computer and the equations of gravitational lensing what the mass had to be to give you that image. And when you do that, you get images like this. By the way, this is not from the same objects, from a different Hubble Space Telescope image, but I particularly like this one. So what this tells you, this is where the mass is at different locations in the sky. This is, the mass is sticking up here because you've got galaxies. This isn't a cluster of galaxies this time. So you've got all this mass here, but then you've got additional mass even in between the galaxies, so there's more dark matter in between the galaxies as well. All right, so we had rotation curves, we had lensing. I have to tell you about the bullet cluster because this is a really cool one. There's two clusters that collided, okay? And what's interesting is that different types of matter behave differently when that collision took place. The atomic matter, the stuff like us, what happens if you and I collide? We don't go very far, right? And that's what happened, whoops. And that's what happened, it's shown in pink. That is gas, it's ordinary gas that got stuck and gives off X-rays. That's how you know it's there. But then there's something else going on because, again, using lensing, you see a different mass that's shown in blue. These are supposed to be arrows. Anyway, so shown in blue, there's dark matter that does not have, you and I have electromagnetic interactions when we collide. There's also strong interactions that hold our nuclei together, and we think dark matter doesn't have those, so it just keeps going. It feels gravity, so eventually it'll come back and settle into a normal-looking object once this collision process is over. But there's very clear evidence of two different types of mass here. Then I also think it's interesting to point out that without dark matter, we would not exist. Because you'd say, all right, well, this stuff is around. Yeah, it's holding our galaxy together, but what more does it do? Well, actually, ordinary matter early on was unable to clump together because it was ionized, and then photons or particles of light would stream out, and they'd pull out the ordinary matter. Ordinary matter was unable to clump early on. Dark matter, nothing stopped it, okay? It collapsed, it was able to collapse earlier into structures. So these are from a numerical simulation, a computer simulation, going back when the universe was about 25 times more, the length scales were 25 times shorter than they are because the universe is expanding. So you go back in the early universe and you watch dark matter particles, shown in blue, and what do? Well, they're not completely homogeneous. There are some regions that have more dark matter than others, and those regions that have more mass collect even more. And so they grow, as I'll show you in the next couple of slides. So you see the dark matter clumping together, and this is, in the computer simulation, this would be today, and it's a pretty good match to what the universe looks like today. There are these filaments of structure with the galaxies at the intersections of these filaments. And then after this form, first the dark matter forms these protogalaxies, and then the ordinary matter can fall in and give us our homes, our ability to support life. I've shown you some of the evidence for dark matter, but there's a whole lot more that I haven't had time to talk about that are just shown briefly in these pictures. And yeah, it's there. So this pie chart is what we think the universe constitutes, and now I want to turn to the question of, well, what are the pieces of the pie? In particular, what is the dark matter? So a long time ago, people tried obvious candidates, rocks, dust, snowballs of hydrogen, but those would have produced things that should have been observed, so those were ruled out right away. And that includes also small stars, planets, and so forth. And what we're left with is, I guess, it's a plethora of candidates, and they're all beyond the standard model of particle physics. Normal physics does not explain the dark matter. You have to try something new. The focus of this talk will be the two that have the best theoretical motivation that I've listed up here. But first, let me tell you about some of the other ones. So one of them is neutrinos because they exist, okay? They are in the standard model of particle physics, although their masses aren't. Why couldn't that just be the dark matter? That would be the simplest explanation. And, well, it turns out that they are too light. So they also stream out of things, and they would ruin galaxy formation. They would ruin the clumping. Also, there have been discoveries of of the masses, and it's just too small. They only constitute 0.5% of the content of the universe, so they don't cut it. In this list I've got here, I'm not going to talk about them all, but I am going to mention, I'm going to show slides of some people that have been in my group over the years, and one of these is Florian Kühnel, who's done a lot of work on primordial black holes. What are they? Well, they would have been smaller black holes, and they would have formed in the very beginning of the universe. They would have formed if there was some region that had extra mass in it. There was perturbations, fluctuations with different amount of mass in different regions. If you have a really, really overdense region, that thing could collapse into a black hole very early on. Now, why would that happen? Well, maybe there was a transition, a phase transition. You know how water boils and so on. That's an example of a phase transition. Well, if you had phase transitions in the early universe, you could have had these fluctuations that led to the formation of small black holes. This idea has been around for a long time, but it has a resurgence of interest because of the discovery of gravitational waves in 2016 in the LIGO detector. They measured merging black holes as massive as 30 times the sun, and they could be primordial black holes. This is a whole talk in itself, which is not the one I will be giving, but very interesting subject, the gravitational wave discovery. Let me turn instead back to in that slide, I said there were the two best motivated candidates. Those are the ones I want to talk about. The WIMPs and the axions. And the reason that we consider them to have the best motivation is they were not invented to solve the dark matter problem. They were around anyway as byproducts of particle theories that people are working on. So it's kind of like you kill two birds with one stone with these guys. I'm not going to say a lot about axions, but I do want to say that they're light particles, but they still are slow moving, and they would produce the kinds of structures I showed you. And they arise as a solution to a problem in the theory of strong interactions that holds your nuclei together. You automatically get them. That was noticed simultaneously by these two guys, each Nobel Prize winners. And I have to say a little more about Steve Weinberg. He's the guy who recruited me to Texas. He was also Pearl Sandick's postdoc mentor. He's one of the founders of the standard model of particle physics overall, so he was kind of, I at one point told him, many of us think you're the world's smartest living physicist, which, yeah, he was kind of off the charts. So I rave about this guy. And unfortunately, he passed away a few years ago in 2021. And in his honor, we now have the Weinberg Institute for Theoretical Physics that I have to mention. I'm currently the director. And we have some interesting activities, so pay attention to if you want to hear some interesting lectures or conferences or whatever. But now getting back to axions, and you have a local expert, Gustavo, is here. He's on the faculty at University of Utah. And Luca Vizzanelli was my postdoc, but before that he was a graduate student here. And this is so I'm showing, I'm not going to talk about the theory, I just want to show really quickly the basic point of this slide is that there are efforts everywhere. People are searching, experiments are going gangbusters in looking for axions. And he wrote a review about this. So, okay, so now I'm going to change to the other topic of the other top candidate, WIMPs. And what that stands for is weakly interacting massive particles. So what does that name mean? Well, first of all, a reporter asked me, how often does one of these hit your nuclei? And we ended up writing a paper on it. So billions pass through your body every second. And somewhere between one a day or one a month hits your nuclei, once per month hits your nuclei, and you are all still here. Okay? Let's talk about cosmic rays and what it does to you to live in Salt Lake. Those are electromagnetically interacting particles. Those can be dangerous, but not here. And airplanes, yes. Anyway, so so these particles, as I mentioned, they don't give off light, so no electromagnetic forces, no strong nuclear forces, yes to gravity. Well, there are four fundamental forces of physics, and the fourth one is the weak force. So let's postulate we have a dark matter candidate that feels gravity and the weak force. And then we also, how heavy are they? Well, they weigh between 1 and 10,000 times as much as a proton. Okay, so why are WIMPs so popular? Well, the first one is, forget about the equation, but the bottom line is, people call it the WIMP miracle. We can calculate how many there are. In the early universe, it was a bath of particles, and we know exactly how often they interact, and it's kind of unbelievable, isn't it? Standard thermodynamics applied to the early universe works dead on, and that allows us to compute how many of these would be around today. And the answer, if you do that, the answer, and they annihilate among themselves early in the universe, and that annihilation takes place with the weak force. Annihilating means they turn into something else. They don't just vanish. Well, they're gone, but they turn into something else. And how many are left today? If you do the math, it turns out you get the right abundance for dark matter. So that is, ka-ching, that's a big plus. The second reason that the theoretical motivation for these particles is that they automatically exist in various particle theories, including supersymmetry, which predicts that for each particle we know, there's a partner. And people here, Pearl has done a lot of work on this, as has Barmak. He was actually my postdoc in Texas, and he's now here. So of all these particles, the heavier ones decay into lighter ones, until you get to the lightest one is stable, until the lightest of these new particles could be the dark matter. I Did I steal this slide from you, Pearl? No, I don't know. It's a different one. Okay. Well, how do you look for these things? There's three approaches. Make it, shake it, or break it. And the fourth prong, dark stars. And I better not run out of time because that's what I'm doing nowadays. All right, the first way to look for these particles is to make them. So let's go to Switzerland, in Geneva, outside of Geneva. And that's where this particle collider is, the Large Hadron Collider, where there's accelerating protons to nearly the speed of light in opposing directions and smashing them into each other. And this is a ring that's 17 miles around. Pictures. Well, let me back up. The two detectors that we're particularly interested in for this work are the ATLAS and CMS detectors. She was the spokesperson for one of these experiments, and she's now she actually just stepped down as Director General of CERN, but anyway. And then this is what these experiments look like, and you can see this person sitting down here, so that's pretty amazing that these are the detectors. And here's Peter Higgs and the other detector, and you may have, I don't know if you've heard of this, they call it the God particle, which is idiotic, but they did discover it, the Higgs boson, there it is. 125 times as massive as the proton. That's what the LHC did discover, but now it's looking for supersymmetry, smash protons together, create these new types of particles that twiddle over the top, refers to the supersymmetry, and these decay in a chain, until you finally get the lightest one, that could be the dark matter, and that escapes detection, which means you've got some missing energy in this story. So you look for that missing energy. Nothing found yet, which is very frustrating. So what does that mean? Well, that means that maybe you need experiments with higher energies, even bigger. They're talking about, what, 80 kilometer, 70 kilometer things now, or 70 miles around? I don't know, giant things. Or it could be that the way we've been thinking about it is wrong, that the physics is more complicated. The simple models that are now being tested are not good enough, and that's Burl's work. But no matter what you find at the LHC, you still won't be proving you found dark matter, because dark matter has to last the age of the universe, not just long enough to escape the detector. Which leads us to direct detection laboratory experiments. Let's take advantage of the fact that you've got billions of particles flying around everywhere and put a detector to see these things. Well, what would happen is that the dark matter particle would hit the detector, bounce off it, and deposit a little bit of energy that you could measure if you had really, really incredible sensitive experiments, really difficult to do these experiments. But I'm going to take a little detour and talk about how did I get into this field, and I have to tell you about my PhD advisor at the University of Chicago, David Schramm. So this is me at Chicago back in the day. And he was one of the founders of the field of astroparticle physics, got me into this field of dark matter, and he was also a great athlete. He was a Greco-Roman wrestler, Olympic hopeful, barely missed it going to the Olympics. And when he did all kinds of sports, skiing, he would forget the mogul, would be gone after he'd gone through it. And unfortunately, he died flying but before I talk about his demise, let me just say his nickname, Shrambo. But he did take a lot of risks, and he died flying his own airplane when he was like 52. So just like to remind people about some of the seminal figures in my field. Okay, that was me as a grad student. Here's me as a postdoc. This is some of the early work I did on dark matter with these two, David Spergel and Andre Druckier, where we did some of the work that got people building the detectors that are ongoing now, the underground detectors. So I did the Feynman diagram, the particle physics. He did the astrophysics. Andre, I don't know what to tell you about him. He's something else. He's Polish, and he speaks English, French, German, and Polish all at the same time, but he's an incredibly creative guy. Drives you nuts. But so we got people to start building these things, and they have to be deep underground, because you have to get away from the cosmic rays that I mentioned that are actually dangerous to humans, that have electromagnetic interactions. There'd be a lot more of those if you're on the surface of the Earth. You go 2 miles down, and suddenly they don't make it there, okay? So you're able to look for these more exotic particles. Though this is the xenon experiment outside of Italy in a deep tunnel. I got to go inside there last summer. That was really cool. Not the detector, but the tunnel. And then now it's a worldwide effort, experiments everywhere with these underground efforts. Frustrating. Most people are not seeing any, when there's no discovery, it's just so frustrating. But there's one exception, it's the Dama experiment, also in that same tunnel. And they have a claim, I guess I'm supposed to be excited because it's our ideas that they're using, which is that the Earth goes around the sun, as you know, and that means that this count rate should go up and down with the time of year. That's what we predicted, and they see this dead on. There's no question they're seeing an annual modulation. But of course, then the question is it dark matter? I mean, it's not the temperature in Rome. People had a lot of theories what it could be, but they've all been ruled out. So it's a complete mystery. Is it dark matter or is it not? And since other experiments are not seeing the same thing, this is just for fun, showing you some of the principal investigators of different experiments. She's the principal investigator of Dama. She's the principal investigator of Xenon. And then you have Juan Collier saying, I'm a Spaniard caught between two Italian women. These conferences are going to be fun. But they're not seeing anything, and so what has to happen, but you know, they're not seeing anything, but then on the other hand, they're made of different material. Dama's made of sodium iodide crystals. These other things are made of xenon. It's very hard to compare them. So now what's happened is other experiments are also made now of the same material as Dama, and they're not seeing anything. So not to the point of ruling it out yet, but it's getting borderline. And yeah, that's frustrating. Okay, let me tell you about a new idea that we had, which is good for looking for dark matter and also other things. Paleodetectors. Those xenon experiments are made of xenon. We're talking about tons of xenon. They've actually bought all the xenon on the planet at this point, which is a problem for the United States for other things that they want to do with xenon. But there it is. Xenon's very expensive now thanks to the experiment. But instead of having a giant volume, let's use time as on our side. In other words, go deep down and pull up old ancient rocks. They can be small, but they've been sitting underground for 1 billion years, collecting tracks from particles. So you're replacing volume with time. So if you dig these things up from 5 kilometers below the surface of the Earth, and this field of these paleodetector ideas, we wrote some theory papers, which is all, these are some people from my group, which is all well and good. But then these two guys took it a step further. They started gathering experimentalists from all over the world. Next thing you know, there's an annual meeting, and next thing you know, there's funding. So the National Science Foundation has now put in $3.5 million, and the Moore Foundation has put in $1 million, so these experiments are actually happening. And my old place, University of Michigan, is one of the places they've got rocks, they just got an X-ray machine to do simple tests, and they've got the electron microscopes to really get the details. This is happening. You not only do dark matter, but you can also, these can be neutrino detectors. These can also be used to look for as reactors, to test of what reactors are doing, or to look for, you know, evil, not the evil empires, but whatever, bad guys. You can see that the bombs, you can find them with this. So you can do a lot with small rocks. Whether they're above ground or below ground, it's the same technology that's now being worked out. These are nanometer tracks that you're able, it's modern era, you can do it. Okay, just a fun picture from we have these every other year, these great meetings. So we just have fun. Okay, there's another way to look for these particles, that was direct detection. There's also indirect detection. I talked about how WIMPs annihilate among themselves. And because they're their own antimatter, they do that. And I talked about in the early universe, it gives you the right abundance, the WIMP miracle. So here's a picture of 2 dark matter particles annihilating through a chain of other particles. And at the end, what do you get? You get neutrinos, high-energy particles of light called gamma rays, and positrons. That's the antimatter for electrons. And there are experiments So indirect detection means to look for these things when your detector is looking into regions where there's a lot of dark matter. This would be going on. I will show you the same process can power stars. I'll get back to that. But on this indirect detection side, they're looking for neutrinos, and here you got to go 2 kilometers below the South Pole. The phototubes, very incredible technology. And they are seeing a lot of interesting neutrinos, very high energy stuff. They're learning a lot, but no discovery of dark matter yet. And then above the space station, they thought they'd nailed it. They thought they'd found dark matter, but no, they didn't. But this one, the Fermi Space Telescope, is looking towards the center of our galaxy. There's a lot, the way the dark matter is spread out in galaxies is that there'd be a lot more at the center than there would be farther out, which makes sense. It's gravitationally attracted towards the center. So if you look at the center, what do you see? Well, they do see extra particles of high energy particles of light called gamma rays. Here's the gamma ray sky that they, whoops, I keep pushing the wrong button. This is the gamma ray sky that they see, and that's the center of the galaxy right there. There's these big bubbles which are interesting, but has nothing to do with dark matter. But smack very close in the very center, there is an excess. You subtract off everything you understand, and there's extra. That could be dark matter annihilation. This is still a big debate, is it or isn't it? And it's a difficult question to answer. So anyway, so there's hints of detection there. Yay, I have time to talk about dark stars. Okay, so the idea here is I have to tell you right away that these things are made of ordinary matter, okay? They're made of hydrogen and helium from the Big Bang, because the first stars formed when the universe was a few 100 million years old. Oh, I forgot to say, the universe today is 14 billion years old. So it's a tiny fraction of the age of the universe when the first stars formed. And there was nothing around other than hydrogen and helium. All that stuff, carbon, blah, 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 was formed much later. So we had this, so these things are made of hydrogen and helium almost entirely, 99.999%, but they're powered by dark matter. So they're not made of dark matter. Okay, so I'm going to repeat that, but I also have to say, so the three of us started this work. Doug Spoliar, me, and Paolo Gondolo, who is a faculty member here. And yeah, we didn't know about, we called them dark stars, misnomer as you'll see, but that was based on, there's 2 songs, one of them by Crosby, Stills, Nash & Young, that was the real reason, but people always assume it was the Grateful Dead song. But anyway, and then afterwards we learned about this cult film. It's terrible. But it is a cult film, so you decide for yourself, okay? And so we originally had the idea, and since then we've had many collaborators. You may recognize somebody here. And so let me talk about the big picture of what these things are. I mentioned they're the first stars to form in the history of the universe, and they'd be powered by dark matter annihilation instead of by fusion. And they could last for a very long time. And a sort of summary that they can grow to be very large. They could end up being 10 million times as massive as the sun, 10 billion times as bright as the sun, leading to 2 interesting consequences. One, because they're so bright, they could be seen in the sky, and we now have candidates with the James Webb Space Telescope, which is the successor to the Hubble Space Telescope, so I'll tell you about that. The other great thing about having very, very large early stars is when they die, they turn into supermassive black holes, which there's tons of them very early in the universe and now, and how the heck were they formed? Well, we have seeds for them, and so these are 2 interesting consequences of getting these supermassive stars early on. Okay, so how did they form? Well, you have 200 million years after the Big Bang, you don't have galaxies yet, but you have proto-galaxies. They're smaller, a million times smaller, actually, and they have a very dark matter-rich center, as do any of these, as do galaxies. And so what happens there is that you get a gas cloud of hydrogen and helium that cools off and collapses, And in the normal picture in the standard picture of the first stars, it would keep collapsing until it gets really, really tiny, and then grows back, creates mass, and reaches about 100 times the mass of the sun. So that is the standard picture. But the question we asked was, yeah, but what about the fact that there's all that dark matter there? And so here's what happens. So as this cloud is collapsing, well, there's the dark matter annihilation, and those annihilation products I showed you, like the gamma rays and the positrons, those annihilation products would interact. They would collide with the hydrogen, and they would get stuck. They would get stuck inside this cloud. And they would end up essentially heating up the cloud, dumping heat into the cloud, which means that the cloud can no longer cool off and collapse. So it took us a year I was on sabbatical at Berkeley, and it took us a year to figure out how what I just told you in 3 sentences. It took us another year to realize, oh my God, it's not just a halted cloud, it's an actual star. It satisfies the 4 equations of stellar structure: hydrostatic equilibrium, thermal equilibrium. It's a real star. And so what we did at that point is, well, I guess I'll just give you I don't have a slide on this. Well, okay, so when they first form, they weigh about the mass of the sun, but then there's nothing to stop them from accreting more mass, more mass, more mass. Ordinary stars can't do that because ordinary stars are too hot, so they push away everything. These guys are very weird. Their radii are about 10 times the radius of the Earth's orbit around the sun. Okay, that's the radius of one star. It's very, very big and puffy, and it's very cool. The surface is cool. There's nothing pushing stuff away, so it can keep accreting. And it starts out at about the mass of the sun, but it can just keep growing until it reaches 10 million times the mass of the sun, and 10 billion times as bright. And the whole key is that it's cool, which means that it's not blowing off hot material, so it's not preventing further future accretion. Now, I don't expect you to understand the details of this picture, but it's called a Hertzsprung-Russell diagram. So this is the surface temperature of these stars, and this is how bright they are, and we let her rip, okay? So these things get bigger and brighter and brighter and brighter and more massive. And beautiful thing about getting so massive is that when they die, they turn into black holes, which could solve the big black hole problem. JWST, the James Webb Space Telescope, keeps discovering more and more of these, and other observatories. Everybody's seeing giant early black holes, which is a real puzzle for standard astrophysics. People don't know how to do it. Well, take one of these big stars, when it dies, it collapses, you get a 1 million solar mass supermassive black hole. Now those can build up to make 1 billion solar mass black holes in time. But if you started with the standard first stars of 100 solar masses, forget it. It takes too long to merge them together. So I've had a lot of ideas in my life, and you do them on the back of the envelope, literally on the little scrap of napkin or whatever at lunch, and then you realize this isn't going to work. Something kills it. Very rarely do you have an idea, and then somebody comes along and tells you, hey, you just solved a problem. And that's what happened here. I'm like, yay. Okay, and so then a few years after we wrote the initial paper, John Mather, he was the guy he's a Nobel laureate, and he was the one who proposed the James Webb Space Telescope in the first place, tell us what to look for. What are these things going to look like in the JWST? Well, so we did that work, and we made predictions. And in fact, one supermassive dark star would be as bright as an entire early galaxy of stars. And yes, it would be observable. The simple kinds of stuff that we did back then, these are the filters, these flat lines are the filters of the James Webb Space Telescope. That means in different wavelengths of light, what their sensitivity is, and boom, we're predicting that things stick up above that. So in other words, James Webb Space Telescope can see them. So as soon as the data started coming out, we're scouring what is there, what kind of candidates are there, and we found some. These were the first two that we found. So they're in a particular survey called JADES, and the number here, 13, refers to the redshift that tells you how far back in time they are. These are the farthest back in time objects ever seen. Okay, this is amazing. So those were the first two, and now we've got another one. This is redshift 14, even farther back. And most distant object ever observed could be a dark star. Now, what do I mean by there being good candidates? Well, it has to do with their spectra. In other words, how much light are they producing at different wavelengths? We make predictions, and then we compare to what is seen with the telescope, and the black dots are the data, and the solid line is our prediction. So, and these are the, yeah. So it matches is the point. And this cutoff here, where you see nothing, you're below the sensitivity of the filters. That is because between any star and us, if there's hydrogen, neutral hydrogen, it swallows the light, but only the light below a particular, but below a particular wavelength, it's going to swallow the light. And by measuring exactly what that wavelength is, that's how you figure out how far away this object is, okay? Because the wavelength gets stretched in time. So don't worry about the details. The point of this plot is theory, predictions are matching the data. So we got pretty excited. The JWST has found many, many high redshift objects. In fact, that is a problem, because this is a problem. I think I have a better slide on this. Let me see, where is it? Let me turn back to that question. But anyway, so here again, this is again the predictions versus, we have more objects now, and the predictions match the data, is the point of these pictures. Now, if you really want to prove it's a dark star as opposed to an early galaxy of stars, there's a helium line. We have a prediction where in those pictures I showed you, there should be a dip. And that dip would only be there for dark stars, not for other objects. Okay, so on this question about too many massive galaxies in the James Webb Space Telescope, I seem to have lost some of the words. But if you assume that all the high redshift objects they have seen actually are galaxies, then that is a problem with the standard model of cosmology. Those pictures I showed you about galaxies the dark matter clumping together to make galaxies and so forth, that tells you how many there should be of what mass. And it just isn't coming out right. There's too much. There's two massive galaxies that are seen, and too many of them. And so fine, some of those are dark stars. Okay, so in conclusion, dark matter can play a crucial role in the first stars. Though made of hydrogen and helium, they could be powered by dark matter heating. I'll have to say, we originally did this in terms of WIMPs, but we're exploring other types of dark matter, and it can work also. And so because they're so massive, they can be precursors to supermassive black holes. And we have candidates in the data, although we need to find this smoking gun of this helium line to really prove it. They're also detectable in other telescopes. And it's interesting to imagine if you find dark stars, that this would be a way to learn about the nature of dark matter, too. Well, I talked about many ways of looking for the dark matter: the direct detection, indirect detection, collider searchers, searching for dark stars. In the last few minutes that I have, I will say a few words about dark energy, the 70% here that is not understood, and that's an impossible problem, both from the theory point of view and from the observational point of view. This is a tough one. Okay, so all types of matter have one thing in common: gravitational attraction. Ordinary matter, dark matter, the definition of matter means gravitational attraction, okay? But this other thing has the opposite behavior. It's somehow causing the universe expansion to accelerate. So not only are galaxies moving apart from one another on the average, they're accelerating apart from one another on the average. So this dark energy, has some kind of repulsive behavior. The theory for understanding that is really, really difficult. So I've had some ideas how to do it, and a lot of other people have too. But it's really a puzzle. And it ties back, ironically, to Albert Einstein, who put into his equations a term that he thought was going to stabilize the universe, make it static. Well, not really. That same cosmological constant, if looked at differently, actually causes acceleration. It could be. So his quote-unquote biggest blunder could be what we're observing here. He called it his biggest blunder, but maybe it's real. Now, on the observational side, it's also very difficult. We are looking for time changing. Is it a constant amount of dark energy? Does it change with time? And we have Kyle Dawson here, who's part of the DESI experiment that is looking for this time changing of the dark energy experiment. But really all we only know really that, dark energy is something repulsive it looks like it's causing acceleration of the universe. And so I'm going to end with a joke. So this was at a World Science Festival in New York. The three of us talking about dark matter. These three guys talking about dark energy. And there's only one thing we know about. So please notice, dark matter, dark energy. Okay. The only thing we do know, dark matter is attractive, while dark energy is repulsive. Okay. Then now to my last slide. This is my book, The Cosmic Cocktail, 3 parts dark matter. And here's my list of ingredients. It's just for fun. And I also, I made a mistake. I should have brought copies of the book, and I've done a book signing while I was here, but they're in my office. I didn't bring them. Well, okay, so we were proposing that there's going to be a sign-up sheet. Oh, it's right over there. So put your name, your email, and what we're going to do is if we get enough requests, I will sign to the people. If you want it made to Joe, I'll say to Joe or whatever. And then you'll pay with $20 via Venmo, and I will send a box of these books back here, and you have to pick them up here. I can't mail them individually, okay? So this is a little convoluted, but if you'd like a signed copy, that's how we're going to do it. Now, Amazon does sell it, so if you don't care if it's signed or not, just go to Amazon, although they after the last lecture I gave, they ran out, but now they have 20 copies again. So, but they're supposed to get more, I don't know, so. But I have plenty. If you'd like me to send a box here, I can do that. Okay? Okay.
All right, thank you so much, Katie, for that amazing talk. We have time for a couple questions, and I'm gonna send the mics around, so I see some hands up in the audience already. Please wait until you get a mic, though, and then we'll see where the ambassadors go with the mics, and we'll call on you.
I'm going to the very top first.
Can I ask the question?
I have no idea who's where, because all I see is bright lights. Oh, here, okay.
Right here, yeah. Can you hear me?
Yes.
Okay. I'm not a student of physics, so I have a
Make a little closer to your mouth.
I'm not a student of physics, so I have a couple of naive questions. One is, what was there before the Big Bang? Because we know that nothing comes out of nothing.
Wait a minute. You think that's a naive question? That's the hardest question there
there
is. I don't know.
Has there been a resolution?
Well, we try. Let me tell you what people try all kinds of ideas.
Yeah.
So here's one. If string theory is correct, as the fundamental explanations, particles wouldn't be the smallest objects, strings would, okay? And the vibrations produce particles. If that's correct, it only works, it's only self-consistent mathematically if there are extra dimensions. There have to be 10 dimensions, not the ones just the ones we know about. And, wait, what was your question? What? Oh, before the Big Bang. So imagine, so here's an example. We live on a three-dimensional surface in this higher dimensional universe. You can think of it like the top of a drum, right? So here's us on this membrane. And Jesus, I forgot the question again. You can tell all this energy comes out of you when you're speaking, and then you just go, whoa. So let me try.
Before the Big Bang.
Before the Big Bang. Thank you. Oh my God, I can't believe it. I can't remember. So what if there's another one of these membranes, and at some point they smashed into each other, and that heated up ours, and that started the Big Bang? That's an idea. There's a lot of ideas out there. This is not a silly, naive question. It's a very difficult, interesting one.
The late-night comedian Jay Leno once gave an answer to this question.
Oh.
With a smirk, he said that before the Big Bang, there was a dinner and a movie, anyway. So that's not the issue.
I think Fred Hoyle, the guy who came up with the name, I think that's what he had in mind.
So I have another naive question. What are the chances that there may be any life form in the universe somewhere besides our planet?
Oh, of course there is.
How do we know that, and how could you find it?
Well, okay, so how do I know that? Well, so first of all, I assume you're only interested in intelligent life, or do you care if there's lichen somewhere else?
Any life, and of course intelligent life.
And, well, so famously, there was something called, there was a guy named Drake, there's a Drake equation. To predict the probability of life elsewhere, you multiply a bunch of things together. So how many stars are there out there? How many of those have planets? How many of those da-da-da-da-da-da? And so one of the major pieces that has changed in the last couple of decades is that every star has planets. It looks like most of them have solar systems. So the locations, the amount of places where life could exist is enormous. So in our own galaxy, we have, what, 1 billion stars? And in the rest of the universe, I don't know how many. And et cetera, et cetera, et cetera. And they keep finding more, so the chances keep going up, let's put it that way.
Okay.
So I'm giving you my personal belief, of course there is. What makes you think we're so special?
Right. Thank you so much.
Oh, I do want to say the following, however. The idea that there have been aliens visiting us, I think, is preposterous for the following reason. If aliens are smart enough to get here, then they're a lot smarter than we are. So they're not going to be very interested. In fact, you know how you little kids squash ants? I'm not interested in drawing them here so they can squash us. And it's like if we can't even be nice to whales. I'm serious. What makes you want to bring these people here, these things, whatever they are, intelligent life forms, they're more intelligent than us if they can get here.
Thank you.
This is all my opinion.
Okay. Quick question.
Wait, where is this person?
Right here.
Okay.
Over here. Our
Okay,
team.
over here,
Okay. The conservation of energy and matter in atomic material, is that the same? Or does dark matter have that same interchange between?
Oh, yeah.
It behaves
Yes.
the same.
Yes.
Oh.
Yes.
And that
That's
was-
when I say particles annihilate, they're not, that energy is converting, they convert into other things.
So then why is one of them, why is dark energy? I mean, do they ever interact?
Another interesting question. Whether people on the average, we assume that they don't. That the cosmological constant I was talking about, that's a vacuum energy. It's not a bunch of particles. And when I say vacuum energy, I don't mean emptiness. It's a real thing. It can be measured. This is called the Casimir effect. If there are two parallel plates, then the vacuum in between them actually attracts them, and that has been measured. So in this room, there is vacuum energy based, and what we really mean by it is antiparticle pairs popping out of the vacuum and then disappearing into it again almost instantaneously. And as I said, but this is measured. This is a real thing. And so that's what people think is the origin of the dark energy is. That's the vanilla model. Well, but that would be okay, except the theoretical calculations of all these of all these contributions from all these particles would be too large by a factor of 10 to the 120 in the exponent. So the theoretical calculations are off by 10 to the 120. Yeah, so that's kind of a problem. So this vacuum theory is not a theory yet.
Okay, so the next one
Hi, I'm waving my hand.
I see you.
So with our observations of dark energy, dark matter, you mentioned there being cosmic rays and interference like that being a confounding variable in retrieving data. Could there be other confounding variables such as maybe the changing of space and time through gravity? Could that be throwing off our data as well?
I don't think that is one, but there certainly are plenty of others. A big one from dark matter experiments is radioactivity. Radioactivity produces spontaneous fission, so you get neutrons, which look exactly like, they weigh the same, they interact the same as the particles that we want to study. So you have to figure out how the hell do you subtract that off or get rid of it. Neutrinos, for that matter, we call these the different backgrounds that we have that you have to eliminate somehow. So there's plenty of them, and the big one is always radioactivity. The detector you're building is radioactive. Your body is radioactive.
Thank you.
Mm-hmm.
Are black hole stars dark stars?
No, they are not. So people are, let me think, what are black hole stars? That people are talking about those again lately. This is another way to, I don't know too much about them. Do you know anything about them? There's a few people working on it, so it's not an insane question. It's just not something I know that I know anything about. So, but it's completely different. So it's a black hole. I know there's a black hole in the middle of it, and stuff and gas around it. Okay, that's what I'm guessing it is. But it's completely different.
All right, and then
The
right
one
here.
question, though, the kid stumps the speaker.
So I've got a bit of a two-parter here. The first one would be, what do you make of the new findings from the DESI that suggest that the expansion of the universe might be slowing down?
Yeah. So, well, not the expand. Yeah. So that's this. I was mentioning this that Kyle Dawson is here. He's a faculty member, and he's a member of this DESI experiment. Oh. I'm sorry, but I don't know what he thinks about that particular result. But many of us think it's wrong. So I have a paper with my collaborator Yun Wang where the trouble. It's kind of, I'm going to get technical, but the way they get these answers is parameterizing the data in terms of the equations of state, what it is today and its first derivative today, and we think that parameterization is bad, and I think that's leading them to the wrong answer. What we did instead was go directly from the data to the energy density, and the significance of the result is much less. So it's too technical, I know, but I don't believe it.
So I guess the second part of my question would be, would you be able to definitively disprove that by measurements of like nucleosynthesis? Like if dark energy wasn't at a constant from the beginning of the universe, wouldn't the models that we have of
Okay, so dark energy was
nucleosynthesis-
irrelevant early on.
It was.
Yeah.
Okay.
So if it really is a constant vacuum energy, early on it was relativistic particles dominated, and then as I'm going forward in time that way. Okay. So
Yeah,
relativistic particles dominated, became less important. Then relativistic were first, then non-relativistic, but they're getting less and less important. The volume expands, their contribution goes down. Eventually, the thing that's constant wins. That's very recent.
Okay.
So you have to look at, yeah.
Thank you.
Maybe one more question? Over here.
Yeah, before I'm unable to hear the questions entirely. Yeah.
Okay. Hi.
Hi.
Earlier you were talking about the Big Bang and how it happened in like a bunch of spots. So how does that relate to the Big Bang singularity?
Yeah. So the notion of a singularity as everything being condensed to one point that's just wrong. But going to extremely high density, to the point where we can't calculate anything, that's really the point. Well, actually, the point is the wrong word to use here, but that's like in the interior of a black hole. So it really means like in the interior of a black hole, it would be an infinite density also. So the singularity in the interior of a black hole. Is there one or not? We don't know.
Okay. I want to thank you all for your awesome questions. I also want to thank Katie
Yeah,
for
no
an amazing
kidding.
talk.
Good questions.
Incredible questions. Thank you so much. So I have a few housekeeping items. The night is not over. So first, I want to invite you to the Zipser Auditorium, just out the backside, or you can come around on the lower level as well, where there's going to be a dessert reception. And we're using this as an opportunity to show off a lot of the other really cool things that are happening in this building. So I don't know what the weather is right now, because I've been in here, but it was looking pretty promising. So if the weather is good, I invite you to go up, and you can go up anyway, to the 4th floor for some stargazing at the Willard Eccles Astronomy Observatory. We'll have some hot chocolate up there. I hope you'll find something cool up there, even if you can't see the stars, but I hope that you can see the stars while we've been in here. On floor 1 of this building, so that's the level that you came in up there, just around here on this side is the Wilkes Center for Climate Science and Policy, and that space is open. There is someone in there who can answer questions and tell you a little bit about the cool stuff that they're doing there and the impact that it's making across the state and across around the world, actually. And then last but not least, we actually have a cloud chamber in this building, which is down here on the lower level. So if you come out these doors here, there's a cloud chamber, and Professor Tim Garrett of the Department of Atmospheric Sciences is there, and he can explain to you what's going on in the cloud chamber, which I think will be really awesome. So please take a look at all the amazing things we have in the building. If you need help finding anything, please find someone with a red shirt, or any of us who kind of look like we know what we're doing. And I hope you enjoy the rest of your evening, and let's thank our speaker again.